fuck? Greetings. Projectile motion without air resistance. The first video of the series. Series would roughly have around, I would say, 2 to 3, 4 more videos max. And since this is a very easier topic compared to projectile motion with air resistance, I genuinely believe you guys will soar through this. Okay, so projectile motion, where the hell did it come from? Well, there was this simple guy, right? His name was Galileo, and he basically said, if I throw a cannonball, oh shit, pardon my language. If I throw a cannonball right here, directly upwards, it's going to have a parabolic shape, right? And why do you think that? Because, you know, it's a very intuitive approach to anything. It like if you throw something up, and assuming it's elastic, and assuming it has no air resistance, it's going to be a parabolic shape. And he went like, imagine if there's like a little ship over here. That's a house. Okay, imagine if that's a house, right? And you have a cannonball, and he shoots it at the house. Well, we have an angle theta, and some diagonal force. Let's call it V of Z, right? We have a diagonal force. He says that if a projectile is shot at an angle theta at a force, it will take a parabolic trajectory. And he stated this in his 1600s, and he described it mathematically a year later. And we will soon come up with these equations of motion, first deriving, and not only deriving, but applying to these in practice problems later on in the videos. All right. So, projectile motion equations. Projectile motion equations. Right. Forgot a little I there. Okay. Well, let me first introduce the basic concepts. What is a vector versus a scalar quantity? We all know that a scalar quantity is only a number, a magnitude. A magnitude is just a number, just a quantity of something. So we can state this as a magnitude, and anything which is a vector, just draw this arrow down here, has a magnitude, obviously, but it also has a direction where it's moving. Let's say if you have a speed of 5 meters per second, you know, that's a quantity. But if you have a 5 meters per second north, if you give the direction and your magnitude of speed, you will then associate that speed as a vector. We all know that. And direction. Right. So we all know this definitions of a vector versus scalar quantity. Right? So how did this guy over here, just chilling, right? He's just chilling about projectile motion. How the hell did he derive all this shit? To make sure that his equations of motion are correct, especially later on in the video once we see they are correct. And let me just skip the page. Yes, all right. I will now start deriving the projectile motion equations. Right, but before that, I will give you a little quiz. Not a quiz, but something to let you be reminded about, alright? So, the difference between V meters per second versus V with an arrow on top meters per second. We all know the difference. If it doesn't have an arrow on top, that means it's a scalar quantity, obviously. If it does have an arrow on top, that means it's a vector, okay? So it's a vector if it has an arrow on top. That means it has a direction and a magnitude. But you know, during our college years, we're always kind of describing speed as the letter S. Well, in this case, I'll be using speed as a letter V without the arrow on top. Okay, without the arrow on top. And I'll tell you why. It's because velocity is the vector quantity of speed, and velocity is obviously denoted as V with an arrow on top. But In this case, we'll be using S as a displacement. Okay, we'll be using S as a displacement because why the hell not? Because why the hell not, all right? Don't worry about this equation. This, I know, just cut out this sort of stuff, right? I'm using let S, capital S, of course, equal to displacement. Now remember, in this case, S is a vector quantity of, S with an arrow on top is a vector quantity of distance, right? And the vector quantity of distance is displacement. So I'll be using S with an arrow on top. Okay. Just going to rub this out. We all know stuff. Okay. Right. Now, suppose you have a velocity time graph, right? This is a velocity time graph. Right, a velocity time graph. And you have to now give a random scenario. Suppose it starts over here and it goes in a linear rectilinear motion and ends up all over here, right? I forgot to label the axes. Meters per second, and we got seconds. All right. So let this point over here equal to v. Let this point over here equal to u. All right, and let u equal to initial velocity. Right. Right. And we let v equal to final velocity. Now, if you haven't already realized, a velocity time graph has a property where if you find the gradient of this line right here, of this line, it gives you the acceleration, right? So in this case, if we find the derivative, it gives us the acceleration, right? It gives us the acceleration, and we know that acceleration is a vector quantity. So, you know, we know that a derivative is the gradient of this line. So the gradient of this line would give us v minus u over the time, which is t, which gives us a. So we can write that v dash is equal to v minus u over t is equal to a. So we know that acceleration is the average change in motion over a period of time. And obviously it's given in meters per second, right? Which can also be given as meters per second, meters per second squared. Oh, ms negative 2. Right? So now we know that the acceleration is the gradient of this line. But now we want to find distance, you know, if you're trying to chuck a projectile at something or someone, for instance, you got to know the distance where you're chucking it at. You know, you can't just throw something at someone who's like 400 kilometers away because, you know, you'll be an absolute downy if you do that. And trust me, you don't want to be a downy in physics. All right? So what you do over here, this is a dot point, by the way, no fucking letter. We know that the property of a velocity time graph is that if you find the area under the curve, it gives us displacement. We know that while suppose you have a distance over, you know that you've seen this triangle before. It's some random basic triangle stuff. You know, this is the scalar triangle, right? Where you have distance, you have speed, and you have time, right? And if you substitute this into the vector quantities, you have a vector triangle, and you have displacement, because you know the vector quantity of distance is displacement. You have velocity, and you have time. And if you know that velocity times time gives you displacement, then you know that the area under the curve is displacement. Why? Suppose I draw another one here. Suppose it has a very velocity doesn't change, it remains constant. Doesn't rise, doesn't fall. Right? This is u, this is v. Suppose. If you know, now what's the area, what's the formula for a normal area? For like a rectangle in this case, it's length times width. So it'll be v, because v is the distance here, right? Times time, right? It's going to be v times time. In this case of the trapezium here, since it has a slant, it's going to have a different sort of, it's going to turn out differently because it's a different shape. The area is going to have different sort of formulas. So I'm going to rub this out. All right. So now we know the difference, or the reason why the area under the curve is a displacement time graph. It is a displacement in a velocity time graph. So now let this little figure over here equal to the displacement, right? So let me just draw this shape, which has been shaded over here, right over here, right? You've got like a little trapezium looking thing, right? And let this be a, actually no, let this be v, in fact, and let this be u, right? Okay. All right. So as you guys know, the area of a trapezium, the formula is a is equal to half a plus b h, where in this case a would be here, b would be here, right? And they're both interchangeable, so it doesn't really matter the order of operations you do it in. Half v plus u h. In this case, the h is going to be this length over here. Compare it to this graph over here. H is going to be time. So this is going to be time. This is going to be time. And now the area under the curve we all know as S. So S is equal to half v plus ut. And let me just remove this. There you go. And I will just move this a bit up. Alright. So we have enough space to work with. So now I'm going to write equation 1 as S is equal to half v plus u t. And we have equation 2 of acceleration, obviously, as v minus u over t. Now, Galileo, where's Galileo? This bloke over here, he went like, damn, bro, like, this acceleration formula right here is like so interchangeable. I can change this formula to like v equals u plus at, and u is equal to v minus at. He got two different formulas just by rearranging the acceleration formula. Now, if you look closely into the first equation, we have two variables within here called v and called u, right? So what we can do now, it's a very long process. I'm actually going to snippet this. Cut this, and I'm going to put it on the next page. Oh, there you go. There you go. Perfect. So now we have two equations. We have v equals u plus at, and we got that by actually rearranging this formula. I'm assuming you know your algebraic formulas. When you have v minus at as, let's suppose, equation 3 and equation 4. Right. Now let's suppose we have equation 5, and in equation 5 we sub in equation 3 into this formula. So we have S, sorry, I forgot the little arrow. S is equal to half u plus at plus u t, right? And then we get a formal answer as half 2u plus at multiplied by t. And this would give us a final answer as what? Not final answer, I'll just do it step by step. Plus at multiplied by t all over 2, which gives us a ut, because the 2's cancel out, obviously, plus a at squared over 2, because the 2 cancelled out the u. Alright. So now we have equation 5. Alright, we have equation 5, ut plus half at squared, or at squared divided by 2. It doesn't really matter how you write it, but you can write it in any sort of way. Okay. Now suppose we have equation 6, and this time we sub in the initial velocity. The initial velocity is u, and let's do that. S is equal to half v plus v minus at now, multiplied by t. So this gives us half 2v minus at multiplied by t, which in the end, step by step, 2v minus at in brackets t over 2, which gives us a vt, because the 2's cancel out on this side, but not on this side, remember that, minus half a t squared, or vt minus v, it's not fucking working, vt minus a t squared over 2. And that's another formula which you can use. So far, let's highlight the things we have got. Where's a highlight? Let's focus on what we have achieved. We have achieved this formula. Why? How the hell did we achieve that? We basically, what we did is that we rearranged acceleration. We also rearranged acceleration to get this, so we can highlight that as a formula. I highly recommend doing this one as a formula too, as you will go through your physics exam in the A League especially. This will come exemplary. I would highly recommend this one. This one's a must, obviously. And this one's a must too. Okay. Right. So now I'm gonna, so we have this one, we have this one, this one, this one, this one. Now I'm gonna do one more. Let's now get back into the acceleration formula, right? V minus u over t, that's the acceleration formula. Now, what happens when we substitute t into this formula right here? This formula right here. What happens when we do that? What do you think will happen? Let's see. Well, if we substitute t, we just have to swap these two terms. So t is equal to v minus u over a this time. And we know the formula for the previous one is s is equal to, make sure I draw my arrows. I drew my arrows, nice. S is equal to ut plus half a t squared. Right, now substitute t wherever you go. It's going to be a long process. So unlucky. V minus u over a plus half a and v minus u over a whole squared. Eventually, I'm not bothered to do this, but eventually you're going to come to a point where you're going to get v squared minus u squared is equal to 2 multiplied by the acceleration multiplied by the displacement. Okay, and you can just chuck this on the other side to get v squared is equal to u squared plus 2as. Okay, so let me just write down all the equations we've got today. S equals half v plus ut. S equals half v plus ut. We also have a second equation of acceleration. A is equal to v minus u over t. Alright. We have third equation. S is equal to ut plus half at squared. We have a fourth equation. S is equal to vt minus half at squared. fifth equation is this one right here. I'm going to label v squared minus u squared is equal to 2as. Right, so these are your equations of motions, where in the later videos you will be shown how to apply regardless of where you're starting from. Let's suppose you're on a little mountain over here and you chuck it at an angle and it lands on someone's dick right here. Someone's head. That's not a head. I'm gonna put him on the head real quick. Alright, he's on his head. Now he's dead. If I chuck it at angle theta, now he's dead. Literally. Suppose you have a height over here, right? In this case, this height is the vertical displacement, right? Obviously, you've got to be a downy to not understand that. But it is the vertical displacement. Okay. Now, if we look closely, suppose you start on the ground, because clearly, if you observe, why is this guy below the ground? No, he's not below the ground. You're just on a hill. Okay, you're on a hill. And suppose this is, let me remove this h. Let me label this whole thing h. The distance above the ground, right? Distance above the ground. And this distance, obviously, label it 400 meters, 500 meters. It's going to accelerate down at the speed of gravity, and you will soon realize the real applications towards these. But in this video, I've shown you how to derive the basic equations of motion. And if you also may have realized a little trend over here, suppose I have 2 points, and I label this vector as x. Alright, you start from point 1 and you end at point 2. What is this? It looks like a function, similar function. If you know how the graph y equals minus x squared looks like, it kind of looks like the same thing, right? Kind of looks like that. And how the hell do we know that? Because we've seen these type of trends in our day-to-day lives, and we've seen that the equations of these graphs have similar properties. So how the hell do you think we can derive or find out the equation of this parabola? Let me show you how. Alright, I'm going to now change the template to a blank template. Actually, let's see what template looks the best. The best template, I do agree, has to be this one. Drawing wise. Okay. Right, suppose you have a projectile motion trajectory, right? At angle theta, at a velocity of, this is the velocity by the way, because you're chucking something in a diagonal force. Let's say we have velocity 1. Suppose velocity 1, right? And this is point 2, this is point 1. And how the hell, from the stuff we're given here, how the hell can we go beyond and find the equation of this whole parabola over here? Okay. Well, what you do is that this is a big point. It's a very clustered point over here. And it's really annoying. It's really annoying, and you know that too. Suppose you enlarge this triangle into its vertical and horizontal components, right? You have a diagonal force here, you have upward force here, and you have a horizontal force here. And by definition, we know that V1 is a diagonal force in any projectile motion. Well, what are these? Like, we know that angle theta is over here. So what do we do with these little people over here? Right, let's call this side x. Let's call this side y actually, and let's call this side x. Right. So what do? Let's break down this whole velocity over here into its horizontal and vertical components. All right. So we know that sine theta is equal to y, the opposite, over v1. All right. You got to be downy to not understand that. V1. All right, and you can solve from there, where y is equal to sine theta multiplied by v1. Now, so that's your y component, right? Now you have got your cos theta is equal to your x component over v1, not v1. Yes, I'm a downy. So x would have to equal to cos theta multiplied by v1, right? So, now you got your vertical and horizontal components. Now, we've seen in our previous pages, one thing I forgot to mention here is that this displacement is undefined. Like, we don't know if it's diagonal, we don't know if it's horizontal, we don't know if it's vertical, right? So how do we know that? Like, if we have an equation over here called S is equal to ut plus half at squared, then how the hell do we know if we're looking at the vertical component or the horizontal component? Well, what we do over here, let's label this displacement thing as S of x, right? The velocity in the x direction, right? Which gives us the u, initial velocity in the x direction multiplied by time, right? So I need to write my t's a bit better. Time, right? Plus, that's not better, half a acceleration in the x direction by the time squared, right? Now, is there some sort of force pulling this projectile towards point 2? No, there's not any sort of force or any sort of like external acceleration source which is pulling it off. Therefore, acceleration has to equal to 0. We can then conclude that the displacement in the x direction is equal to the initial velocity in the x direction multiplied by time. Suppose we solve for time. We know that S of x is equal to t is equal to S of x over u of x. Now, u over x is initial velocity. Suppose we take the u of x as there, because u of x is equal to the horizontal component of this velocity vector. So how, if we sub this formula in right now, this arrow is going to be pissing me off. If it's cos theta multiplied by v1, make sure you don't get any complex conjugate things. People do get mixed up, I don't know how. Yep, therefore t has to equal to this whole thing right here, right? So I don't know why I wrote this again. Now, time is constant within the s direction and the y direction, so we can continue writing the displacement in the y direction. The displacement in the y direction is equal to the initial velocity of the y direction, which, remember, equals to y, plus half acceleration in the y direction, t squared, right? Now, acceleration in the y direction is, you've got this big-ass earth thing, and it pulls shit down, right? Or in other words, if you want to go Einstein level, the fabric is pushing you down or something. And, I'm being a downy over here, but if you sub in this time over into this displacement into the y direction, how the hell, what can we do? Like, what can we do? Okay, so suppose you have S of y is equal to the u of y into the S of x over, let's just let cos theta times v1 equal to, let's suppose, alpha, right? So we know that this whole denominator over here equals to alpha, so we can just write alpha over here, plus a half negative g, because you got to be downy to mess that up. I keep on saying downy, sorry for saying that. S of x direction, the displacement in the x direction, multiplied by alpha, right? And remember, time squared. Okay, now I'm going to select this whole thing and bring it all into a new page. Copy, new page, paste. Right, beauty. Nice. All right. Now you got this whole new equation. A lot of expanding to do. All right, a lot of expanding to do. So let's just bring this down. All right, now I'm going to write it in full form. So I'm not going to say it as alpha. I'm just going to name it as it is. Okay. S of y in the y direction, displacement in the y direction is equal to the initial velocity in the y direction multiplied by the displacement in the x direction over cos theta multiplied by v1, right? Velocity in the diagonal direction. So we have plus, since this g has a negative sign, we can say that it's a minus, right? Minus half g, and now for the ultimate expression, displacement in the x direction squared over cos squared theta multiplied by v1 squared. Right. And now if we somehow manage to substitute u, so we know that the initial velocity in the u direction, in the y direction, is sine theta multiplied by v1, right? So sub that into this whole equation, and we basically get S of y is equal to sine theta multiplied by v1 over cos theta multiplied by v1 in brackets, and we can always multiply this by S of x minus half g, and this as S of x squared over cos squared theta multiplied by v1 squared, right? And we can always, as you know, in a normal Cartesian plane, the reason why we call this x and this y is it shows displacement, it shows distance, right? It shows the rate of where you're moving, the point at where you're moving. And suppose you're moving over here, let's say x point y, you draw a little line over here, right? There's a reason why at this point xy you can state that as also S of x, S of y, because you're S of x and S of y. Therefore, in this whole equation, let me just rub this out. In this whole equation over here, I can name S of y is equal to sy, and S of x is equal to x, right? I suppose. So we know that y is equal to tan theta, because we know sine over cos is tan. These two cancel out. Tan theta multiplied by x. So tan theta x minus half gravity x squared over cos squared theta v velocity squared, right? Right. So now we have a final equation. Tan theta x minus, now gx squared. Comment if you think, if I've done some mathematical error, please correct me. But, you know, it's a little bit of rearranging and then basic algebra rearrangements. Oh, let me just go back. And you've got 2 cos squared theta multiplied by 2 v1 squared, right? And we can leave it in factored form, but I'll leave it in factored form. 2 tan theta x, right, minus gx squared over 2 cos squared theta multiplied by v velocity squared. And there is your equation to your parabola. Let me select this. Select copy, paste it into a new one. Oh. Yep. Alright. Oops, wrong pen. Alright, so we let y is equal to some function of x